InternLM-XComposer 2.5-OmniLive, a comprehensive multimodal system for long-term streaming video and audio interactions. Pan Zhang and others. Shanghai Artificial Intelligence Laboratory, the Chinese University of Hong Kong, Fudan University, University of Science and Technology of China, Tsinghua University, Beihang University, Since Time Group. Abstract. Creating AI systems that can interact with environments over long periods, similar to human cognition, has been a long-standing research goal. Recent advancements in multimodal large language models, MLLMs, have made significant strides in open-world understanding. However, the challenge of continuous and simultaneous streaming, perception, memory, and reasoning remains largely unexplored. Current MLLMs are constrained by their sequence-to-sequence architecture, which limits their ability to process inputs and generate responses simultaneously, akin to being unable to think while proceeding. Furthermore, relying on long contexts to store historical data is impractical for long-term interactions, as retaining all information becomes costly and inefficient. Therefore, rather than relying on a single foundation model to perform all functions, this project draws inspiration from the concept of the specialized generalist AI and introduces disentangled streaming, perception, reasoning, and memory mechanisms, enabling real-time interaction with streaming video and audio input. The proposed framework, InternLM-XComposer 2.5-OmniLive, or IXC 2.5-OL, consists of three modules. 1. Streaming Perception Module. Processes multimodal information in real time, storing key details in memory and triggering reasoning in response to user queries. 2. Multimodal Long Memory Module. Integrates short-term and long-term memory, compressing short-term memories into long-term ones for efficient retrieval and improved accuracy. 3. Reasoning Module. Responds to queries and executes reasoning tasks, coordinating with the perception and memory modules. This project simulates human-like cognition, enabling multimodal large language models to provide continuous and adaptive service over time. All code and models of InternLM-XComposer 2.5-OmniLive are publicly available at the GitHub link. Introduction. The goal of developing AI systems that can understand and interact with environments over long periods akin to human cognition has been a central focus of research for decades. The rise of large-scale data corpora and multimodal large language models has driven significant advances in free-form multimodal question answering. Recent developments, such as Mini-Omni, Video LLM Online, and Vita, have made notable strides toward enabling more natural and immersive online interactions. However, challenges persist in creating systems capable of continuous interaction due to the intrinsic limitations of a single decoder-only large language model architecture. Existing architectures encounter significant limitations in real-time and long-term streaming perception, reasoning, and memory. The sequence-to-sequence decoder-only architecture used in current MLLMs forces a switch between perception, for example, seeing and hearing, and thinking, limiting the simultaneous processing of inputs and outputs. Additionally, existing works rely on the integration of multimodal memories within context windows. The reliance on long contexts to store historical information proves impractical for long-term use, especially in scenarios requiring continuous AI assistance. Multimodal data, like video streams, can quickly accumulate millions of tokens within a few hours, making it impractical to maintain context over multiple days of service. The context and inefficiency of storing all historical clues within the context further limit the system's capacity to provide continuous and long-term service. In contrast, the human brain can effortlessly integrate perception and cognition, preserving long-term multimodal memories. This is believed to be closely related to the functional partitioning design of the human brain cortex, where different areas of the cortex are responsible for different tasks, such as perception, memory, and cognition. Inspired by the paradigm of specialized generalist AI, we propose a system, InternLM-XComposer2.5-OmniLive, composed of fused specialized generalist models for streaming perception, reasoning, and memory, respectively. The system is designed to enable AI models to engage continuously with environments while retaining observations over time. By integrating short-term and long-term multimodal memory, our approach attempts to emulate human-like cognition, enabling more dynamic and sustained interactions. As shown in Figure 1, the IXC 2.5-OL system consists of 3 key modules. 1. Streaming Perception Module. This module processes the multimodal information stream on the fly. To ensure perception accuracy and efficiency, the video and audio streams are handled separately. A live video perception model processes the video stream, encoding the information and storing key details in memory. Meanwhile, an audio model recognizes the contents of human speech and other sounds, for example, barking, knocking, or whistling. It triggers the reasoning process when human queries occur. Multimodal long-term memory module. This component integrates both long-term and short-term memory, enabling the retrieval of detailed short-term information as well as long-term historical cues. It continuously compresses short-term memories into more information-rich long-term memories to enhance retrieval efficiency and accuracy. 3. Reasoning module. The reasoning module, activated by the perception module, handles queries and performs reasoning tasks. As a component with the most model parameters, it serves as the core of the system's deep cognitive processes. The proposed system empowers AI with the ability to perceive, think, and memorize simultaneously. By overcoming the limitations of alternating perception and reasoning, IXC 2.5-OL seeks to provide continuous adaptive service and long-term AI service. The proposed system will not only enhance the performance of AI assistants, but will also contribute to the broader AI applications capable of continuously interacting and adapting to dynamic environments. The IXC 2.5-OL demonstrates strong performance across both audio and video benchmarks. Among the open source models, IXC 2.5-OL achieves competitive results on audio recognition benchmarks such as Winit speech for Chinese and Libra speech for English. For video understanding benchmarks, IXC 2.5-OL achieves state-of-the-art results among models with less than 10 billion parameters, obtaining an M average of 66.2% on MLVU and an overall accuracy of 68.7% on MVBench. Additionally, it demonstrates competitive performance on video MME and MMBench video. On recent video streaming bench, IXC 2.5-OL achieved new SOTA results on open source models, highlighting its exceptional capabilities for real-time video interactions. To foster the development of the multimodal streaming interaction community alongside the model parameters, the inference and deployment source code encompassing both the web frontend and backend code has also been released. All code and models of IXC 2.5-OL are publicly available at the GitHub link. Related works. MLLMs for text-image conversation. Large language models, LLMs, have garnered significant attention for their remarkable capabilities in language comprehension and generation. Building on this success, large vision language models, LVLMs, have been developed by integrating LLMs with vision encoders, extending their ability to comprehend visual content and enabling applications like text-image conversations. Earlier, LVLMs were primarily designed for single image multi-round conversations, whereas recent advancements have expanded their capabilities to process and understand multi-image inputs. MLLMs for video understanding. In addition to advancements in image understanding, the field of MLLMs has seen growing effort in video analysis. To address the complexity of video inputs, existing approaches leverage techniques such as sparse sampling or temporal pooling, compressed video tokens, and memory banks. Additionally, some methods utilize language as a bridge for video understanding. Beyond these video-specific strategies, video analysis can also be framed as interpreting a high-resolution composite image generated from sampled video frames. Recent advancements have increasingly focused on online video understanding, aiming to simulate real-world scenarios where AI processes video streams in real time to comprehend the environment on the fly. However, existing solutions still lack the capability to simultaneously perform perception, memory, and reasoning, limiting their applicability for consistent and long-term human-AI interactions. MLLMs for audio understanding. Audio understanding can be effectively modeled as a sequence-to-sequence task, which enables powerful integration with large language models by incorporating audio tokenizers and encoders. In addition to receiving the audio input, recent research investigates streaming duplex speech models that allow speakers to interrupt freely. Beyond audio text models, emerging research delves into audio-visual models and unified architectures that process audio, visual, and text modalities. MLLMs for omnimodal understanding. Integrating multiple modalities into a single omnimodal foundation model represents a promising research direction. Existing works explore models capable of processing omnimodal inputs, typically combining video and audio to produce outputs in various formats. These outputs include text, audio, and omnimodal contents. In the current design of IXC 2.5-OL, we handle the audio and video modalities separately to mitigate potential influence during joint training. In future versions, our model will incorporate joint training across all modalities, enabling seamless omnimodality integration. Method. As we briefly introduced in Section 1, the IXC 2.5-OL has three disentangled modules. The streaming perception module for on-the-fly visual and audio information processing. 2. The multimodal long memory module for memory integration and retrieval. And 3. The reasoning module collects information from the perception and memory module and handles queries and performs reasoning tasks. All the modules work simultaneously and interact asynchronously. Streaming perception module. Besides nature language, the IXC 2.5-OL could handle video and audio natively. To realize this, the streaming perception module contains an audio translation module and a video perception module. Audio translation module contains an audio encoder, an audio projector, and a small language module, SLM. The audio encoder encodes the input audio sample into high dimension features, and the audio projector further maps the feature to the input space of the SLM. The SLM outputs both the class, for example, laughing, clapping, or raining, of the audio, and the natural language within the audio, like the automatic speech recognition. In practice, we use the Whisper model as the audio encoder and a Qwen 2 1.8 billion parameter as the SLM. The training contains 2 stages, and we list the training data in Table 1. Video perception module provides coarse-grained visual information to the multimodal long memory module. It processes the real-time video input stream and encodes each frame into semantic features. For efficiency, we use the OpenAI Clip L14 in practice. Multimodal long memory module. The multimodal long memory module is the core design to handle extremely long video input and helps the reasoning module to get rid of millions of tokens from its context window. It shares a similar idea from the video streaming that encodes video clips into short-term memories and integrates them into long-term memory. With the given questions, it retrieved the most related video clips for the reasoning module. Formally, the multimodal long memory module is trained with 3 tasks. Video clip compression. With features of K sub th video clip extracted from the perception module, F sub k is an element of the real numbers to the power of t times n by c. We initialize its short-term memory, H sub k is an element of the real numbers to the power of t times p by c. By the spatial downsampling and its global memory, H hat sub k is an element of the real numbers to the power of 1 by c. We realize the compression by the autoregressive and feature aggregation nature of LLMs. H sub k and H hat sub k are equal to the compressor applied to the concatenation of F sub k, H sub k, and H hat sub k. Memory integration. Short-term memory represents the detailed information of each short video clip, while the model still lacks a macro view of the video. To this end, with the short-term and global memory of a list of video clips, we integrate them into long-term memory by the compressor in the following format. H bar 1, H bar 2, up to H bar k is equal to the compressor applied to H1, H2, up to HK, H hat 1, H hat 2, up to H hat k. The H bar equals the matrix formed by H bar 1, H bar 2, up to H bar k as an element of the real numbers to the power of k by c. Represents the video in a high compressed way, and we denote it as the long-term memory. Video clip retrieval. When users raise questions, the multimodal long memory module retrieves the question-related video clips and provides both the video clips and their short-term memory to the reasoning module. In practice, we first encode the question to the feature space of the memory. We concatenate the long-term memory with the tokenized question as the compressor input, and we view the last token of the output features as the memory space aligned question feature. Then we calculate the similarity between the question feature and each video's global memory and select the most related clips for the reasoning module. Implementation detail. We use Qwen 2 1.8 billion as the 3 LLMs and construct several kinds of training data for the 3 aforementioned tasks. As shown in Table 2, we train the video clip compression task with short video captioning data from multiple sources, using the same prefix captioning task designed in video streaming. For the memory integration task and video clip retrieval task, besides the off-the-shelf video grounding data, we also construct data for 2 unique tasks: semantics implicit question and reference implicit question. The semantics implicit question means the question does not point to some object directly, but mentions the usage or meaning of the object, and the model should find out the object by understanding the implicit question. For example, when the user asks, "How about the weather today?" the model should find out some weather-related object in the past video stream, such as an umbrella, a sunglass, or something. Another example could be, "I'm hungry. Where can I heat my sandwiches?" The model should find the microwave oven it has seen before. The reference implicit question means the question uses pronouns rather than nouns. For example, what is this means the models should retrieve the current frames, although it does not mention any exact objects. Both kinds of implicit questions are commonly used in real-world communication, while current models fail to handle them, so we construct corresponding training data to empower the model with these capabilities. Reasoning module. The reasoning module is initialized by an improved version of InternLM-XComposer 2.5. And we add a memory projector to align the memory feature with IXC 2.5. For given questions and both visual and memory information provided by the memory module, we formulate the input as question. Here is the question related to the video clip. Here is the question related memory. In real-world usage, there exists some noisy input that should not be answered. For example, the user says in or okay. The model should keep salient and wait for the next question. To realize this, we add an additional instruction prediction process for each question to decide if it should be answered or not. System pipeline. As illustrated in Figure 3, the system comprises the front-end SRS server and back-end server. The front-end application, developed with JavaScript, enables the camera and microphone to capture video and audio stream inputs, which are then pushed to the SRS server. Concurrently, it establishes a WebSocket connection with the backend to listen for audio outputs and interrupt signals. When audio data is received, the front end plays it. Upon receiving an interrupt signal, the front end suspends the audio playback and discards the pending audio. SRS server, simple real-time server, is a straightforward and efficient real-time video server. Adept at supporting a multitude of real-time streaming protocols such as RTMP, WebRTC, HLS, HTTP, FLV, SRT, and others, it is renowned for its ability to reliably receive and deliver audio and live streams. Backend server. After establishing a WebSocket connection with the front end, the backend will pull streaming from the SRS server and initiate separate threads to read audio and video. The audio reading thread will segment the audio stream into 4096-bit chunks and enqueue them into the audio queue. The voice activity detection (VAD) thread continuously reads data from the audio queue and detects the start and end of voice activity. Upon detecting the start of voice activity, the backend sends an interrupt signal to the front end to pause the currently playing audio, and at the same time dispatches a backup signal to the video process, directing it to save the current memory state. When detecting the end of voice activity, the entire voice segment will be enqueued into ASR to do queue. The ASR thread continuously reads audio segment from ASR to do queue, performs background noise classification and voice recognition on them, and then enqueues the results into LLM to do queue for use by the LLM. The video reading thread reads video frames at a rate of 1 frame per second and enqueues them into frame queue. The compressor process reads video frames from the queue, recognizes them, extracts relevant memory, and stores it. Upon receiving a backup signal from the VAD thread, the compressor process will save the current memory state for later retrieval. The LLM process reads text from the LLM to do queue and determines whether it is an instruction that requires a response from the model. For texts identified as instructions, the compressor process will use the current instruction and the backed up memory to perform memory grounding in order to retrieve memories related to the instruction. The LLM process will then generate a response based on the retrieved memories and the instruction, and encode the resulting output into TTS to do queue. An additional TTS thread will convert the text from the TTS to do queue into audio and send it to the front end. Experiments. In this section, we validate the benchmark performance of our InternLM-XComposer2.5-OmniLive, including both audio and video benchmarks. Audio benchmarks. We evaluate our audio models on two prominent automatic speech recognition benchmarks: Win-It Speech for Chinese and Libra Speech for English. Win-It Speech includes two test sets: TestNet, which represents high quality and relatively clean Chinese speech, and TestMeeting, which captures more challenging conversational scenarios. Libra Speech consists of 4 splits: Dev Clean and Test Clean, which contain clean, high-quality English speech, and Dev Other and Test Other, which include noisier, more complex utterances. As shown in Table 3, our IXC 2.5 OL demonstrates superior performance compared to recent streaming audio LLMs, such as Vita and Mini Omni, particularly achieving lower word error rates across both Chinese and English benchmarks, with merely a lightweight 1.5 billion parameter LLM. Video benchmarks. In tables 4, 5, 7, and 8, we compare IXC 2.5 OL with both closed source APIs and open source models on conventional video understanding benchmarks, including MLVU, Video MME, MMBench Video, and MVBench. Furthermore, we also assess the performance of different models on the recently proposed streaming bench, which is designed to better evaluate performance for real-time video interactions. The results of this comparison are presented in Table 6. For the video benchmarks, the base model utilizes 64 sampled frames for each video during evaluation. MLVU. MLVU is a comprehensive benchmark designed for evaluating multimodal large language models in long video understanding tasks. The videos range from 3 minutes to 2 hours and include 9 distinct evaluation tasks. Here, we evaluate 7 multi-choice tasks, including topic reasoning, anomaly recognition, needle QA, ego reasoning, plot QA, action order, and action count. The detailed comparisons are given in Table 4. The IXC 2.5 OL exhibits state-of-the-art performance among closed-source APIs and open-source models with parameters less than 10 billion, surpassing the previous standard state-of-the-art performance by 1.3% for Video XL, 1.6% for GPT-4o. Video MME is a high-quality video benchmark. The videos are collected from 6 primary visual domains with 30 subfields to ensure broad scenario generalizability, encompassing both short, medium, and long-term videos, ranging from 11 seconds to 1 hour. As demonstrated in Table 5, the IXC 2.5 OL exhibits competitive performance on this benchmark, comparable to previous state-of-the-art Mini CPM V 2.6. Streaming Bench. Streaming Bench is a streaming video benchmark designed for real-time video evaluation. It comprises 18 tasks showcasing 900 videos and 4,500 human-curated QA pairs. In this context, we focused on assessing visual understanding in real time. Table 6 illustrates the comparative analysis, demonstrating that IXC 2.5 OL excels among all open source models, achieving a 2.67% improvement over the previous state-of-the-art model, LLAVA1 Vision, and falling just short of the closed-source API, Gemini 1.5 Pro. This performance solidifies IXC 2.5 OL's remarkable prowess in real-time video interaction. MM-Bench Video. MM-Bench Video is a free-form QA video benchmark consisting of 600 videos and 2,000 QA pairs. The duration of each video varies from 30 seconds to 6 minutes. Given the open-ended nature of the answers, the benchmark utilizes GPT-4-based evaluation to enhance quality in terms of accuracy, consistency, and alignment with human judgment. The results are presented in Table 7. IXC 2.5 OL demonstrates state-of-the-art performance on perception tasks and comparable performance on overall evaluations. MV-Bench. MV-Bench is a video benchmark that emphasizes temporal understanding. It encompasses 20 challenging video tasks that cannot be effectively addressed using a single frame. As shown in Table 8, IXC 2.5 OL, despite having a smaller 7 billion parameter size, has outperformed both the GPT-4 series and the 72 billion open source model LLAVA1 Vision, demonstrating its strong capability in understanding video temporal dynamics. Conclusion. We have presented IXC 2.5 OL, a real-time streaming model that advances multimodal text, audio, and visual capabilities with long-term memory. IXC 2.5 OL empowers users to engage in dynamic and interactive experiences. Our model's real-time processing enables fluid and responsive interactions, allowing users to engage with ever-changing environments of multimodal data seamlessly, providing a more intuitive and efficient user experience. Our future work will focus on reducing system latency to provide a seamless user experience. My summary. This paper introduces InternLM-XComposer2.5-OmniLive, a multimodal AI system designed for continuous, long-term interaction with streaming video and audio inputs. Inspired by human cognition, it separates and synchronizes three key components: real-time streaming perception, long-term multimodal memory, and reasoning to handle ongoing environmental changes. By integrating a memory compression technique and enabling simultaneous perception and thinking, IXC 2.5 OL achieves strong results across various video and audio benchmarks, pushing forward the capabilities of multimodal large language models in long-term real-time applications.